motion diagrams. So what is a motion diagram? So in order for us to understand motion, what we do here is that we go in and we analyze the strobed motion of an object. So what we do here is that the strobed motion of an object is essentially the history of that motion. So what this is here is that we analyze motion using strobe lights. And what do I mean by strobe light? Well, what does a strobe light do? What it does here is that so a strobe, what it does here is it uses a series of flashes. And as it uses a series of flashes, what it does here to show the history of an object's motion. And what I mean by that is that look at this image that I got off the web. So if I paste this, you could see that I have this image of a boy running from left to right. And what I'm going to say here, to make it nice and simple, I'm going to say that each flash is 1 second apart. Is that true? No. They're much smaller than that. But in this case, I'm going to say that they're 1 second apart. So now remember what I said before. We want to make motion as simple as possible. So what do? We take the boy and we reduce the boy to a what? A single point. What's the best point that we could use for the boy? Well, we wanted center's mass. Where's the center of mass of a boy? It's most likely around his belly button. So then I'm going to come in here and I'm going to focus. So I need to reduce to center of mass, mass point. And so what I'm going to do here is that I'm going to look for his belly button. So if I look for his belly button, I'm going to say that maybe his belly button's right there. Right there. And I'm just sort of like guessing where it's at. But I'm looking something like this here. So now, if I have his belly button and I now put him down to a flash like this, look what happens now. Now, I know that each flash is 1 second, so look what happens here. So as I come down to here, I know that this is 0 seconds. So then, as I come down here, you could see that I can draw lines. And what you're seeing here is that these dots have a particular pattern, right? So this is 0 seconds. This is 1, 2, 3, 4, 5, 6, 7. So by counting the dots, I know that this motion has taken 7 seconds. Okay, so when I'm looking at this, so now instead of drawing this picture with the boy, what am I going to do? I'm going to put dots like this. And what you're seeing here is that when you look at the definition of velocity, look what happens here. Look at this here. If I look at this distance, let me move this down a little bit. So if I look at the distance between this dot and this dot, Let's call that delta x. Now look at the distance between this dot and this dot. It's about the same. And if you look at the distance between this dot and this dot, it's exactly the same. So that means here, so when I look at my definition of velocity, velocity says it's delta x over delta t. But if delta x is a constant, why is it a constant? Because you could see that it's roughly about 2 squares. And then the time is a constant. Why is it a constant? Because each flash takes 1 second. You could see here that the velocity must be also a constant. So constant velocity implies that the dots, the strobe images, are equally spaced dots. So constant velocity implies equally spaced dots. So if I start to count them now, right? I could go like, so from 0 to 1, that's the same distance. From 1 to 2, that's the same distance. From 2 to 3, that's the same distance. So now I come in and I draw my velocity vector. So what do I know about my velocity vector? Well, my velocity vector goes from 1 to 2. And that tells me what the speed is at point 1. Now, oh, I should be very careful. What I said was incorrect. The velocity at 1 is represented by the distance right here. Let me be careful because this is tricky. So the speed represented at point 1 is the interval between 0 and 1 divided by 1 second. So when I draw that velocity v1, note that it is not represented by the interval between 1 and 2. So that means this is speed 1. So when I look at speed 2, speed 2 is represented between the interval 1 and 2. So if I was to start to write this, I would write it like this. This should be the interval between 1 and 0. And when I look at the interval for 2, it should be the interval between 2 and 1. And then V3 should be between 3 and 2, and etc. So, but if I just draw the picture, okay, so now the motion diagram for constant velocity is something like this. So that means I have my dots, and they're equally spaced dots. So that means that my arrows, assuming constant velocity, are going to have this length here. And when I look at this velocity right here, you could see that this velocity is v, and it has this amount of displacement for that amount of time. However, if I look at these dots, you could see that the dots are farther apart. So when I draw these velocity vectors, you could see that they're going through what? I have a bigger velocity. Why? Because I have a bigger distance, but my time interval is the same as before. And so when I draw these, you could see that these guys are going to be bigger velocities, whereas these guys are going to be smaller velocities. So my motion diagram tells me how fast this object is moving here. So what do I mean by constant velocity? So constant velocity then implies that I have constant speed, constant direction. That's what I mean by a motion diagram for constant speed. Constant velocity. We started talking about motion diagrams. And one of the things that I said here is that a motion diagram is a strobe light image, which is a series of flashes. And these series of flashes then show a history of an object's motion. Each flash shows two pieces of information. There's the time lapse between two flashes, which we define as 1 second. That's not true for a camera or a video. We'll start videoing experiments here in a little bit, and you'll see that typically it depends on your either your cell phone or the camera that you're using. They could be, a 1/10 of a second, a 15th of a second, but we're going to assume that they're 1 second. Then there's also a spatial separation between these two. So in other words, if there's a small distance like this delta x that's red, then I draw a little delta x. But if I see a big separation between the dots, then that's a bigger distance. And that's how we measure speed then. So when I'm looking at this, we started talking about constant velocity. Now this is super important here. This little detail, this first image that has the red, green, blue, and violet colors is important. And the reason why it's important is because it really sets up how to draw or conceptualize motion correctly. So here we go. I'm assuming that the motion starts at 0. Now, when I look at point 1, I have velocity v1 that's in red. But v1 is the interval before the dot at 1. It's between 0 and 1. And therefore, when I talk about the velocity v1, I'm talking about the distance between 1 and 0. So when I look at the velocity at 2, you could see here, because it's green, it's the space before point 2, between 2 and 1, and then et cetera, et cetera. So the motion, that is the speed or velocity, is determined by the interval before the point. That is important when you start to really look at the motion diagrams as we're going to be looking at them today. So then, ignoring that, you could see that if I go to the image below, you could see that if I have a slower speed, I have smaller distances between the dots. So therefore, I have a smaller delta x, which I drew in green. And if I look at the faster speed, you could see that the dots have a larger distance, and you can see that I'm drawing a bigger delta x. So that means the reason why it's a slower speed is because it's covering a smaller distance. The reason why it has a higher speed is because it's covering a farther distance. But note that I tried to draw the delta t's the same size. Why? Because the time intervals are 1 second, and they're always 1 second. That's constant velocity. Now let's talk about change in velocity. So when I look at change in velocity, there are two ways that you can change velocity. I could either change the speed while keeping the direction constant, or I could have constant speed but changing direction. This is a tricky one for some people. People always assume that if you're changing velocity, it's always about changing speed only. Not true. If you're changing direction, that's also a change in velocity. So let's go for that. So what we found here is that if I have constant velocity, then this tells us is that essentially Nothing ever changes. And what I mean by that is that the length is always the same and the direction is always the same. So if I'm going to change speed, then that means that the length of the vectors must be getting longer. So if I draw that out, then you could see here is that if I'm speeding up, what that means then is that my dots have to be getting farther apart. But if they're getting farther apart, that means if I look at this speed here versus the next speed or the next speed or the next speed, what you're seeing here is that here you could see that I have a small distance, but over here I have a larger distance. So even though I have the same amount of time, you could see that this automatically tells me that I'm going to have what? I'm going to have, in this case here, I'm going to have a smaller speed, then it's getting faster, faster, and faster, right? So I'm getting the difference in these things, right? And I could say the same thing and you know, in the other situation. The other way that you can change your speed is if you're slowing down. So if I'm slowing down, oops, wrong color. So if I'm slowing down, you could see that instead of the dots getting farther apart, they got to get closer together. So if I'm looking at these things, then the strobe image tells me this here. Now let's be, you know, I should have done this in the previous one. Let's be careful here. I cannot draw the dots on a single line here, okay? And the reason why is that they're going to overlap on each other, okay? They're going to overlap on each other. So let me explain to you what I mean by this. Well, look at this. If I try to draw them right on top of each other, look what happens. So let's play that game that we did before. So I'm going to label this 0, 1, 2, 3, 4. So if I try to draw them right on top of each other, then I have to look at the distance for this interval right here. So note that in this interval, this distance is big. So that means that the velocity here has to be big here. That's at 0.1. Now, when I look at this interval here, you could see that that interval now is then smaller. So this velocity has to get smaller. Now, a lot of textbooks, what they do here is that I'm going to come back and I'm going to change what I drew here. Okay? I'm going to change what I drew here because I realize I'm not being clear. What they try to do here is that because this is 1, 2, 3, 4, they'll try to draw this thing 4 squares. But you see how these guys overlap? You can avoid that if you try not to draw dot to dot. Dot to dot, I know, makes it easier to do that. But so what I have a tendency to do here is that I don't try to draw them dot to dot, but I just try to draw them just scaled. So if I do that, then this is a velocity at 1. So when I look at the next velocity, because it's a smaller distance, I should have a smaller velocity. And then I just keep playing the same game here. And then if I look at this interval, wait, yeah, if I pick this interval here, then you're seeing that this guy has to be even smaller. Oops, not 1, but 3. But clearly, you're seeing here that the velocity is getting, you know, shorter in length, but continues to move in the same direction. So one of the things that I wanted to do here is I want to show you an image of this thing here. And what I did here, again, I went online and I did pirate the image. And so when I did it here is that I had a diver, and what I'm seeing with the diver here is that I'm only looking at him roughly at the central peak. And then what I tried to do is I put a dot right where his hip was. And if I follow the hips, you could see that the velocities are getting what? They're getting larger and larger and larger, telling you that he is actually speeding up. That would be a motion diagram for this situation. Now, so if I go to the other situation, we talked about changing speed, constant direction. Now I'm going to go the other direction. And if I look at this situation, now I'm going to be constant speed, and then I'm going to have changing direction.
Carlos, I had a quick question.
Sure.
In regards to the slowing down versus speeding up, I'm a little bit confused on why the concept of having the velocity 1 and slowing down being the distance of like 0 to 1, why that isn't the same in speeding up.
Okay, I'm not really sure what you're saying here, Tessa.
I'm sorry.
So you're saying here, so when you're looking at speeding up right here,
Mhm.
I didn't label them here, so let's label them.
Okay.
So when you're asking the question,
Mhm.
when I'm looking, so I'm seeing these as two separate things.
Okay.
So the scaling doesn't have to be the same. So you're asking me, tell me one more time now.
So on the slowing down,
Uh-huh.
we have the big delta x between 0 and 1, and then that would be the velocity 1.
Yeah.
So why don't we, or is that the same thing for the speeding up one, where from 0 to 1, that would be velocity 1 as well?
I see what your question is. So the definition of velocity is that you need a displacement. I cannot draw a speed on 0 because I have no information what happened before 0.
Mm-hmm.
You can only define velocity when you have an interval. A single point is meaningless when you're trying to talk about velocity. So that's why I can only draw a velocity vector at 1, because now I have this delta x interval now. Is that your question? Or something like that, probably.
Probably something like that. Yeah, I think I just need to like sit on that for a little bit. But thank you.
Yeah, no problem. So in this case here, if I have this, what you're going to find here is that this really talks about turning motion. Okay, it's turning motion. So if I'm driving at a constant speed, we know that we have to have equal intervals. So you could imagine here is that if I'm going to make a right-hand turn, then, I mean, if you're going to make a right-hand turn at a constant speed, then that means that the spacing between my dots should be roughly the same. So I'm going to try to make that length always be the same as I'm turning. But now what happens? I'm changing my direction slowly here. So I'm trying to have equally spaced dots. So now I have to think about my interval here now. So if I think about my interval, you could imagine that if this is my interval right here, and I label this 0, 1, 2, 3, 4, then that means at this point, my velocity must be in that direction. But now look at the direction of the interval here. The direction of the interval is slightly off. So the only way that could be then is that my velocity must have changed direction at point 2. And then you could see that I'm just going to keep playing this game where I focus on that interval right here. And it's looking something like this. And so in the end, you could see that I might be coming into the right-hand turn, but you could see that there's a slight angle still. So what you're finding here is that the direction of motion is always the direction of the velocity. So that if you were going along this curve here, right, you're making a right-hand turn. If for some stupid reason you let go of the steering wheel, right, that would be stupid. Which direction are you going to go? You're going to go in the direction of the velocity. And so, you know, even though you feel like you're being pulled to the left, you're moving towards the door. That's really a Newton's first law thing that we got to talk about later on. But you would literally move tangent to the curve, which is a direction of the velocity here. So what we do here is that to try to clean this up a little bit, then I would say maybe we do this type of thing. So then when I look at my velocity, all the vectors are roughly the same length, but they're changing. So you're seeing a change in direction here. Now, just to give you a sense of what is going on here, what I have here is I have another image, which is, I think is a good image here. And if I bring this up, you could see that we have a woman and it looks like she's on parallel bars. And what you would expect here, just by looking at this image, is that as she goes towards the top, you would think that she would be slowing down. And then as she swings down towards the bottom, she would be going faster. Again, I put the dot right at her hips. And you could see here, well, look at the spacings here. If you're looking at the spacings, we have to agree that her speed looks like right at the top here is probably the smallest right here. But if you're looking at the bottom, that's a much bigger, you know, that separation between those two dots is quite big. So you could imagine that at the bottom, she has to be moving at the fastest speed right there. So again, by looking at these motions, they tell you how fast. By the way, I made a mistake. Let's see if you could spot it. Look what I did at the top. Now note that that green's a terrible color for this. So I'm going to get rid of the top here. And the one thing that you want to remember here is, what did I say here? You have to look at the interval before that. Look at the spacing here. And now compare it to the spacing here. See how the purple is larger? So that means here, so I'm going to take that green one out here. So that means the speed here has to be smaller. It's a smaller interval. When I look at this other interval, the fact that that looks like a bigger interval, that means that her speed here has to be what? Higher than the next interval. And so, I mean, that's an example of turning motion here.